All right, welcome. We're about to take a deep dive into the abstract world of group theory. Now, I know that might sound a little intimidating, but our mission today is actually pretty simple. We're on the hunt for a hidden, stable core that exists inside even the most complicated systems. Let's get right into it.
So let's kick things off with a little puzzle. Just look at this simple cube. How many different ways can you spin it, flip it, and turn it, and have it land looking exactly the way it started? Think about it. This simple question about symmetry is actually our doorway into this whole topic. Every single one of those rotations is an action, a single piece of a much larger system.
Here's the roadmap for today. We're going to take this in 5 steps. First, we'll learn the language of symmetry. Then, we'll use it to find the unchanging core. After that, we'll figure out how to measure commutativity, sort everything into families of symmetry, and finally, we'll uncover a truly surprising truth about something called the inescapable center.
Okay, first up, the language of symmetry. See, if we want to talk about rotating a cube, or any kind of structure really, we need a precise language. We can't just be vague, we need a formal way to pin down what we're talking about.
And the language we use is built on this beautiful idea called a group. A group is really just 2 things: a collection of elements, like all our cube rotations, and an operation, which is just a way to combine them, like doing one rotation right after another. Now, for this system to be called a group, it just has to follow 3 basic rules. The way you combine them is associative, there's a do-nothing element called the identity, and every single action can be undone by an inverse action. That's it. That's a group.
So now that we have this language, we can start our search for that unchanging core. Within this collection of symmetries, are some of them more special than others? Are there certain elements that just seem to play nice with all the others in a really particular way?
Which leads us to this really fascinating question. Within our whole group of actions, are there a few special ones that play nice with everybody else? In other words, is there an action you can do where the order just doesn't matter at all?
Well, the answer is a big yes, and it has a fantastic name: the center of the group. We write it as Z of G, and it's basically the set of all those super friendly elements that commute with every single other element. If an element X is in the center, then doing X then G is always the same as doing G then X, no matter what G is. This is the stable, predictable heart of the entire system. Okay, let's make that less abstract. Think about the group of all invertible n-by-n matrices. I mean, that's a gigantic, complicated beast, where the order you multiply things in matters a lot. But you know what its center is? It's incredibly simple. The only matrices in there are the scalar ones, just the identity matrix multiplied by some number. Those are the only ones that play nice with all the other matrices. And here's the really important part. The center isn't just some random grab bag of well-behaved elements. It has its own structure. In fact, it has the exact same kind of structure as the bigger group it lives inside. It's a group within a group, or what mathematicians call a subgroup. And proving this is just so elegant. To show the center is a proper subgroup, you just have to check 3 things. First, closure. If you take 2 things from the center and combine them, the result is still in the center. Second, identity. The do-nothing element is always in there. And third, inverses. If an element is in the center, its undo move is in there too. It's a completely self-contained, stable little world.
Okay, so we found the VIP section, the elements that commute with everything. But what about the ones that are a little more selective? Let's figure out how we can measure commutativity for elements that only play nice with a few others.
But that naturally leads to another question, right? We've got the center for the elements that get along with everyone. But what about all the other elements? How do we describe an element's personal social circle? You know, the specific things it does commute with. We totally can. It's called the centralizer. For any one element, let's call it G. Its centralizer is the set of all the other elements that commute specifically with G. You can think of it as G's own personal clique, its inner circle. If G is in the center, its centralizer is the whole group. But if it's less social, its centralizer is a lot smaller. And there's this great quote that I think just nails it. The concept of the centralizer can be thought of as measuring how far away an element is from being in the center of a group. A huge centralizer means you're basically best friends with everyone. You're close to the center. A tiny one means you're way out on the fringes. It's a brilliant way to think about it. Now, let's switch gears a little. So far, we've been grouping elements based on who they commute with, but what if we tried to group them by their fundamental type of action? This brings us to the idea of families of symmetry.
And this idea has a name. It's called a conjugacy class. A conjugacy class basically lumps together all the elements that are similar. They represent the same type of action, just maybe viewed from a different perspective. So for our cube, all the 90-degree twists around a face would be in one family, while all the 180-degree flips around an edge would be in another. They're structurally the same kind of move.
Just take a look at this table for the symmetries of a triangle. It's so clear. You can see how every single action falls perfectly into one of these families, or conjugacy classes. The do-nothing move gets its own class, the rotations are sorted into their own types, and the different kinds of flips get their own families. And importantly, there's zero overlap between them.
And that is the big idea here. The entire group can be split up into a perfect, non-overlapping union of these conjugacy classes. It's like taking a giant bag of Legos and sorting them into neat piles. Here are all the 2x2 bricks, here are the 2x4s, and so on. Every single piece belongs to exactly one pile.
All right, we've built up all this abstract machinery, centers, centralizers, conjugacy classes, and now we get to the payoff. Because all of this leads to a profound, powerful, and completely non-obvious truth about the very nature of these systems.
At this point, you're probably asking, okay, so what? Why did we go through all that trouble? And that is a fair question. This is where pure math gets its superpowers. By building these abstract tools, we can discover things that are absolutely, undeniably guaranteed to be true.
And here it is. There's a powerful theorem that says for a special kind of group, called a finite p-group, that's just a group whose total number of elements is a power of a prime number, like 2, 4, 8, or 3, 9, 27. It cannot have a trivial center. It's literally impossible.
Let's put that even more simply. For any of these special p-groups, the size of its center is guaranteed to be greater than 1. It has to contain more than just the do-nothing identity element. There is guaranteed to be at least one other action in there that commutes with absolutely everything. And this is why it all matters. This is the big reveal. It shows that from pure abstract logic, we can uncover concrete, guaranteed facts about structure. This isn't just a pattern we noticed. It's like a fundamental law of nature for these mathematical objects. We used pure logic to prove that a stable core must exist.
So this whole journey, from a simple puzzle about a cube to a fundamental law of mathematical structure, it just shows you the incredible power of abstract thinking. And it leaves us with this final, really exciting question. What other hidden structures are out there, just waiting for us to find them?